Okay, well, we'll start there. So welcome to Scotland's Digital Science Festival. My name is Wendy. I'm a member of TechFest. So TechFest, we run the programme. And really welcome back to those that have been here before. Just a little bit of housekeeping. If you could please keep your cameras off and your sound off, then that would be fantastic. We will be taking questions at the end of the programme, so if you could just pop those in the chat, pop them in as they come to you, but we'll leave those till the end, and Scott's more than happy to answer some questions then. I think I'd like to welcome Scott to TechFest. So it's the first time that you've done something for TechFest, but you're on my list now, so you'll never get away. So Scott is a sound designer, sound editor and composer, and self-confessed sound nerd. He's worked on over 70 feature films, and I was quite impressed. I know we talked about people having their own Wikipedia pages earlier, but I did see you've got your own entry into IMDb, the Internet Movie Database, so that was really helpful for me to find. Great, so well done there. Scott won 2023 Telly Award for Sound Design for the movie Assault on Hill 400. Originally an astrophysicist, but has also been a BBC science journalist and a fellow Scot from Arbroath, as you can probably tell from our mention in the chat. But Scott lives between Los Angeles, which is very exciting, and Arbroath, and he's very kindly joining us from Arbroath this evening. So welcome to the presentation on science fact versus science fiction. And Scott, I'll hand over to you.
Thank you, Wendy. My goodness, what an introduction, eh? I won't fit through the door afterwards, my head's so big. Welcome to Science Fiction versus Science Fact. So tonight we're going to look at a few things that I'm sure we've all been asking ourselves when we watch these films. You know, you watch something on the big screen and you're like, can that actually happen? Can we do that? So this is what we're going to look at tonight. Before we delve into that, I just want to talk a little bit about myself, although I don't think I need to do that now. Thank you very much, Wendy. But yeah, who is this Scott Derwingson-Peacock? Who does he think he is going on about science? Well, I have been into this since I was a wee nipper. I mean, as far back as I remember, I've been into space, monsters, ghosts, you name it, anything that's out there, I've been into. In fact, I don't actually remember this, but Mum tells me the story that when I was 3 years old, we were going to the Braemar Highland Games actually, and it was a really cloudy day, and the sun broke through in a shaft of light, and apparently, this is no joke, I said, "Is that a spaceship come to take me home?" And like I say, I don't remember saying this, so it is entirely possible that I was left behind. I'm not actually human. I'm happy to go along with that. So, of course, my life was kind of set out in front of me from there. And I went to university and studied astronomy and astrophysics, which was fantastic. But the maths was far too hard, so I left that to others. And then I got into journalism and worked in news and current affairs, and then worked in science journalism for a bit. And I worked on a programme called Tomorrow's World. Now, that's not been on for a wee while, but your mum and your dad will remember this programme. It ran for years. And was like showed you all the top science inventions of the day. And then I taught for about 10 years in Glasgow at a couple of Glasgow colleges. Then met the woman of my dreams, which meant I had to drag myself halfway around the planet to LA. That was about 8 years ago. And since then I've been a sound designer and composer for 70 movies, mostly creature features. So Godzilla type movies, zombie movies, space movies, that kind of thing. So to sum myself up in a couple of words, Nerd City. There you go. I wear my anorak with pride and I love it. So tonight, science fiction versus science fact. So we'll be looking at strange new worlds, or rather, how could we actually get to those strange new worlds? You know, we see it happen in TV and film all the time. But is it possible? And how much has science actually influenced what we see? And we'll also look at how would we actually get there. And it largely involves faster than light travel. This is something we see all the time in science fiction. And we'll look at why that's a thing, why that's so important, travelling faster than light. We'll also look at what warp speed is. Now this happens in various different forms throughout science fiction, but it's a trope. You see it happening everywhere. We'll look at wormholes. I'm sure you've heard of that. Black holes, very closely related. And we'll also look at time travel. But to kick off, when we look at all sorts of sci-fi shows, films, franchises, whenever there is a moment when they finally escape the bad guy or they're chasing the bad guy and they make a jump into faster than light travel, there's always some consistency throughout all these different stories, and I'll show you what I mean. So you can see there are three big franchises: Star Wars, Star Trek, Doctor Who. And whenever they make the jump, there's always some distortion, something happening either to the background or to the ship itself. So we're going to look at what that is, because that does actually come from science. It's not just made up. It's not just a thing, a fad, a trend that everyone does because it looks cool. So in order to do that, to look at faster than light travel, we need to look at light itself. We need to ask, what is the speed of light? And what actually is light? So I'll try not to take too much of a deep dive into this, but these are questions that, well, we just accept, really, don't we? You know, we switch on the light. You're seeing me just now because I've got a light coming off a bulb reflecting on the wall, and the camera's picking it up. The screen is sending out light particles, photons, and you're picking them up with your eye. So that's how we see. But what actually is going on there? What is light? So in every beam of light, all light consists of a wave, which has an electric field and a magnetic field. You don't really need to worry about that. But we call it electromagnetic radiation. And electromagnetic radiation is produced whenever there's a change in energy within atoms. That's basically what it is. Atoms change energy levels, and that gives off a wee packet of light, or electromagnetic radiation. Light itself, what we call light, is just the part our eyes can detect. It's a tiny part of the electromagnetic spectrum. And I'm sure you've all seen this at school and so on, but it's just a wee recap. So as we can see, at one end, we've got the long, lazy wavelengths. So this is largely where our communications happen: TV, broadcast, radio. We go up a bit, we got radar, we have microwaves. Our mobile phones actually communicate with microwaves. Have you ever done that thing where you've been on the phone for ages and then your ear gets hot? It's the microwaves. It's not the same microwave frequency as the one you get in your oven, so don't worry about that, but it's still microwaves. And then this little colourful bit here is just a tiny, tiny part of the spectrum, and that's the bit we can see with our eyes. And then beyond there, the energy gets higher and higher until the energy can penetrate skin and muscle, but maybe not so much bone. And this is where your X-rays come in for medical imaging. More powerful than that, we have gamma rays and then cosmic rays. So all electromagnetic radiation travels at the speed of light, or in scientific terms we call it c. Don't know why, maybe it means constant. But all electromagnetic radiation travels at the speed of light. And why is that? What's so important about the speed of light? The thing is, the speed of light isn't just something that radiation travels at and that's it. You can't go faster than light. Nothing can go faster than light. And this is a question that has occupied scientists ever since they realised this, particularly this one here, and I'm sure you'll recognise him. Albert Einstein, the man himself. So he was crucial in this. And of course, we've probably all heard of his theory of relativity, but he had two theories of relativity. In 1905, he published the special theory of relativity, which was about the speed of light and how mass and energy are related. They're not separate things. Mass and energy are related. One affects the other. One can turn into the other. And how the speed of light affects time and mass and energy. That was special relativity, 1905. 10 years later, he develops the general theory of relativity. And this is all about how mass affects gravity. And with the two together, you've pretty much got the whole picture covered, but not quite, as we'll see later on. So special theory of relativity. So what's so special about it? Well, as you can see in this diagram, we have three dimensions. We have forward, we have back, we have left and right, and we have up and down. So you can describe any location using three dimensions, three coordinates. But do we live in a three-dimensional world? And actually, no, we don't. We don't live in a 3D world, because our three dimensions also exist in time. We are moving through time. So we also exist in a fourth dimension. And time is regarded, or you can regard time as the fourth dimension. And this may seem quite strange in sci-fi, but actually we use four dimensions all the time. If you think about it, it's in everyday language, everyday experience. So for instance, coffee, or a date, or you meet your mate at a pub. You can say where, but it's useless unless you also say when you want to meet, right? Everyday common experience, we use fourth dimensional coordinates all the time. Where are we going to meet, and when are we going to meet? See, you're really clever, hey? So our universe, we have length, breadth, height in our universe, and duration. So this is the fourth component, the fourth coordinate in our universe. So fair enough. But Einstein's breakthrough was this. He said space and time are not separate. They're not a different thing, even though we experience them as different. He said we live in a four-dimensional world, but that four-dimensional world is a world where space and time are the same thing, that he called space-time. Actually, it kind of helps if you say that really quickly. Space-time. It's one thing. It's not space and time. It's space-time. 1, 2, 3. Space-time. There you go. So this is now where we start getting into diagrams. Don't worry about it. So imagine if you just have a simplified diagram like this one, where space, all three dimensions of space, are going along this line here, the horizontal line, and time is the vertical line. Okay? Well, you can work out the space-time path of someone. It's a fancy word, space-time path, by looking at their movements through space and through time. So say, for instance, you take a walk to the shops. You might travel a little distance, you see. You've not gone very far, but you've taken a long time to get there. So that's a low speed. Now, like the hand of a clock, you could rotate this round, turn this round to here. If you jumped in a car, say, you'd be going off at high speed, covering a great distance, but in a small amount of time. Bear with me, it's relevant. This is called a space-time diagram, or space-time diagram. And this is the clincher. The faster you go through space, the slower you go through time. The speed of light is absolute. Nothing can go faster than it. But the weird thing is, nothing can go slower than it either. And that's because we all move at the speed of light through space-time. Weird, eh? Just take a wee bit to get your head around. We all move through space-time at the speed of light, even if we're sitting still, like you are just now, sitting still in front of your computer. But because you're not moving through space, you're moving through time as quickly as you can. Bear with me, I'll show you what I mean. So this was first proposed by Hermann Minkowski, who was actually Einstein's mentor. And he came up with this idea that we're all moving at the speed of light. He tried to work out why the speed of light is a limit, why you can't move faster than that. So, say you're leaving Perth and you want to go to Aberdeen. You're going to be going roughly northeast, right? So you're going at 50 miles an hour northeast, but some of that speed is easterly, some of that speed is in a northerly direction, right? So you've got an east component, you've got a north component. If you're just heading east entirely, you're going 50 miles an hour that way, but no miles an hour that way. Likewise, if you head north, you're going 50 miles an hour north and there's nothing east. But if you go diagonally, there's a bit of speed in the east direction and a bit of speed in the northerly direction. But you're slower in both directions, right? You're not going 50 miles an hour that way, you're not going 50 miles an hour that way, you're going 50 miles an hour that way, which is just a wee bit of east and a wee bit of north. Now, imagine we change that to space-time. So you're sitting in a parked car. You're not doing anything, the car's not doing anything, but you're still moving through time. So you're still moving upwards, right? But because we move through space-time at the same speed, all of us, that arrow is the same length. And as that clocks down, as you start driving off in your car, you are moving through space, but you're moving through less time. Yeah, it's pretty mental, isn't it? You're moving through space-time at a constant speed. Now, this is impossible because you're moving through space, spending no time at all. But forget that. So we're moving through space-time, and depending on what direction we're going, depends on how quickly we're moving through space and how quickly we're moving through time. Now, the faster you go through space, the slower you go through time. It's mental, I know. I just wanted to show you that though, because I think it's mind-blowing. But it's true. It's true. The special theory of relativity predicts this, and there is proof that time goes slower the faster you go. And we've done this by putting clocks in space, or really fast jets. So you take two clocks, they're absolutely in sync. You keep one on the ground, you put another one in the plane, jet plane, or the International Space Station. I think they've done both. And the plane, in this experiment, the plane went over to New York and landed, and then they compared the two clocks. The one in New York was slower. This is called time dilation, and the amount it was slower by was perfectly predicted by Einstein's theory of special relativity. So we know it works, we know it's true, but the implications are enormous, they're huge. We use special relativity all the time. It's wild stuff, but it's in everyday things. It's in your phone. GPS, Google Maps can only work with Einstein's equations. So this is how GPS works in a nutshell. You're at any point on the planet, there's loads of satellites around, and they're all pinging the same pulse. Incredibly well synced up. They're pinging the same pulse, and your phone receives these pulses at slightly different times. And it's those slightly different times that tells the phone where you are. That's how GPS works. It's phenomenal. But because they're all moving at different speeds to you, special relativity makes it inaccurate. It wouldn't work unless you could put special relativity into your app to compensate for that. So your phone, your wee phone, you use all the time, uses Einstein's theory of relativity. So that's how we know it works. That's how we know it's real. So special relativity, going back to what we were looking at before, is the reason why we can't travel faster than light. Because we are already travelling at the speed of light through space-time. It's brilliant. That's why we can't travel faster than light. That is, I don't know how you feel about that, those last few minutes, but that is a deep, deep dive into the nature of causality, the nature of reality, why we can't travel faster than light. So there you go. Pretty cool, isn't it? So can we break the speed limit? Is there any way we can get around it? We can use Einstein's other theory. We could use general relativity. So general relativity states that mass and energy can bend space-time. So space-time, you can think of space-time as like a mesh, a four-dimensional mesh. and it warps and changes and moves depending on what we do in it. So mass and energy can bend this space-time. And that's what gravity is. That's what Einstein said. Gravity is not a force like magnetism or electricity. It's a bending in space-time. So we have a planet orbiting the sun. The sun is a heavy object and it creates a well. It creates a well. And so the shortest point across this well is not a straight line, it's a curve. And this is predicted by general relativity, which says that mass and energy are the same thing. So you can bend space-time using a heavy object, but you can also do it with a lot of energy. And this is what spacecrafts do in science fiction. We know it works because we've added general relativity to the Newton's laws of motion, and they perfectly describe planetary movements. And mass and energy are related through the most famous equation in the world, and I'm sure you know it, E equals mc squared. So this, you might have seen this graphic before, but we have to do it in 2 dimensions. We have to imagine space as a flat sheet. But in reality, it's more like this. So this is what they think actually happens when a heavy object moves through space-time. You see the contractions? It squeezes, it pulls. And this is gravity. This is what causes gravity. Now, how does this get us faster than light? If we can bend or stretch or contract space-time any way we want, then we can move quickly across vast distances. So another word for bending or stretching is warping. You see where I'm going with this one?
Warp 6. Warp 7.
So in all these depictions, you see there's a jump into warp space. And there's either some kind of distortion, as I said earlier on. So if you look at these guys here, they're about to shoot off. And there's a wee bit of a stretch going on there. This is a great example of what I mean. So when this one goes off, boom, there it goes. So either the stars are distorting, you can see the background distorting there, or when it goes into warp drive, you can see it distort. So what's happening is, the space-time ahead of the spacecraft is contracting, so it's like ruffling up a duvet, there's less distance to cross. And it's also lengthening the space behind it. And so this is warp drive. This is what actually happens when the Enterprise goes into warp, or the Millennium Falcon goes into hyperspace. You're pulling the space in front of you, space-time in front of you, and you're stretching it behind. So you can only do this because of E equals mc squared, because mass and energy are equivalent. So you have to get the energy together that will warp space-time. So could we build a warp drive? Can it actually be done? Yes, possibly. It's difficult. It's not completely impossible, theoretically. So in other words, we could, but it's kind of beyond our physics just now. But someone has worked it out. In 1994, a Mexican physicist, Miguel Alcubierre, actually sat down and worked out what it would take to create a warp drive. And this is his simulation. This is what is happening in space-time, actually, when a warp bubble is generated by a spaceship. And this is the spaceship. Welcome to the Alcubierre drive. It's a nice name for it. So what the Alcubierre drive does, it creates a warp bubble around the spaceship, a well in front of it which scrunches up space-time, and then a wall behind it which stretches it out. And that, if you were outside the bubble, it would look like the spaceship stretches out as it shoots off into the distance. And that's what we see when the Enterprise goes into warp drive. So the Alcubierre drive is consistent with Einstein's relativity. It doesn't violate relativity, but it does allow us to go faster than light many times. Something like 200 times, I think, theoretically. It's an extraordinary thing. But it's a little tricky. It requires something called negative energy. I'll talk about that in a minute. All sorts of exotic matter that we haven't quite generated yet. Maybe dark matter? Perhaps. But huge energy requirements. We know it requires something like the output of the sun to generate this warp field here. So it's a wee bit beyond us just now, but it is possible. That's the crucial thing. And also, our science fiction acknowledges this. So it's a lot of the sci-fi ideas that you see, the jump into warp drive, coming out of warp drive, hyperspace, all that stuff, is kind of based on fairly sound science, actually. And it all comes from Einstein. He's the guy. So, one way we could actually create a warp drive is if we could harness that kind of energy. And one way we could do that is negative energy. Now, this was discovered, negative energy was discovered in a wee lab, something like in the 40s, I think. And all that happened was an experiment with two metal plates that were very, very close together. There was no charge on them, there was no electric current going through them, there was nothing. And you would expect that there would be equal amounts of pressure, i.e. zero, on both sides, between the plates and on the outsides of the plates. But what Casimir, the scientist that discovered this phenomena, what he found was that when the plates go together, you start to get a pressure pushing on the outside. So in other words, the pressure in between the plates went down less than zero. And he said there was a negative energy going on there. And the way he described it was using quantum physics. So we're moving away from relativity here, which is all big and galaxies and spaceships. And now we're going down into the quantum world, which is subatomic. And I'm also going to share with you something in science fiction that uses this negative energy, this quantum energy. But I've only seen it once. So this is an exclusive for you. Hold the front page. It's only ever been used once before. As far as I know, the Casimir effect pointed towards this huge discovery. And one way of explaining how somehow you could get a negative thing in between two plates was the quantum explanation of vacuum fluctuations. I can't even say it. Vacuum fluctuations. There you go. So the Casimir effect was just a tiny thing that you could easily overlook in a lab, but it could lead us to an infinite reservoir of energy. So we're going to have a look at this by leaving the world of relativity, leaving the very big, and we're going to dive down into the quantum world, into the very small. In fact, not just the very small, but the smallest level theoretically possible in our universe. And down at this level, we encounter something called the Heisenberg uncertainty principle. And down at that level of reality, things are virtual. They might appear, they might not appear. You can't measure exactly where something is or how fast it's going or where it is. There's an inherent fuzziness to reality way, way down at that level. So here we go. We're taking a deep dive. And this is the world as we know it, on the level of about a metre across. I've no idea who Russell is. There's a square inch zooming past us as we go down. There's the ant. And now we're passing the millimetre stage, thousandth of a metre. Smallest object visible to the naked eye. There's the width of a human hair there. And we go down 1,000 times to the micrometre, a millionth of a metre. This is the world of the virus. This is the smallest thing we can see in an optical microscope because we're down to the smallest light wavelength. And we keep going, down, 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 smaller, 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 past the DNA into the world of the molecules. Now we're at a nanometre, a billionth of a metre. There's the water molecule there. It looks a bit like Mickey Mouse. And further down to the atoms in a molecule. That's a 10 billionth of a metre, the angstrom it's called. But we have to keep going. All the way down, a picometer, that's a trillionth of a meter. I mean, how small is that, right? You go further down, a 10 trillionth of a meter. Now we're into the realm of the nucleus. And then we keep going. We keep going. A femtometer. Anything smaller than this is not confirmed. In other words, we can't measure anything smaller than this. We go past the quarks, the constituents of the nucleus. Down, 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 zeptometer, yoctometers. We go all the way down, millions upon millions of times smaller, until we get to this, the Planck length. This is the smallest theoretical length possible. Down here, there is what we believe is the quantum foam. That's at 10 to the minus 35 meters almost. And that is 0.0 with 34 zeros and a 1. It's just impossible to work out, to even conceive how small that is. But at that level, you get this. These are the vacuum fluctuations, the quantum fluctuations. It is a seething inferno down there. It's really, really quite something. If you hold your hands like this, in between, you think it's empty space, apart from the gases in our atmosphere. But even if that was a vacuum, it wouldn't be completely empty, because down at the quantum level, you have this. And what's going on here is we have billions upon billions, countless numbers of virtual particles and antiparticles coming into existence, positive and a negative, meeting and then annihilating. Positive and negative arising, meeting, annihilating. This is happening unbelievable number of times per second. And they're just spontaneously appearing out of the uncertainty principle, out of the basic uncertainty of the universe at this level. They're just appearing, meeting, annihilating. It's happening all the time. Seething. Limitless energy. Now, what if we could collect that? It's been explored in science fiction. What if we could somehow separate the positive virtual particle from the negative one before they meet and annihilate? We would literally be scooping up energy out of thin air. It's pretty incredible. I love this. And it was explored by the author and scientist Arthur C. Clarke in his story, The Songs of Distant Earth. A beautiful story, actually. It was about how mankind set up on another planet, and it got there in a spaceship using the quantum drive. And the quantum drive spaceship did not need to carry any fuel at all. It just scooped up energy from the raw vacuum of space. How? I have no idea. It doesn't explain. But this is a tantalizing idea. It would solve energy problems forever. And it's a possible source for negative energy, which we could use for a warp drive. And we could also use for a quantum drive. So again, theoretically, the warp drive is possible. We can visit other worlds. We just can't do it yet. Maybe we'll never. Maybe the engineering problems will be too great. But I don't know. I like to be optimistic. What do you reckon? So, are there other ways to cheat the laws of physics? How else can we cross space faster than light? Well, one way is wormholes. I'll talk about that in just a minute. Wormholes could give us access to other dimensions, or we could use other dimensions to travel faster. This is huge in sci-fi, actually. Massive. Fantasy as well. You know, I mean, what's Narnia? It's another dimension, right? I'm going to show you a clip now from a film called Event Horizon, which is very scary. Don't really recommend it. Well, I do actually. But it's scary, so if you're under 18, forget it. But this bit is a very good explanation of what a wormhole is, from the engineer who designed it.
The Event Horizon was the culmination of a secret government project to create a spacecraft capable of faster than light flight.
Oh, no, excuse me. You see, you can't actually do that.
The law of relativity prohibits faster than light travel.
Relativity, yes, we can't break the law of relativity. We can go around it. ship doesn't really go faster than light. What it does is it creates a dimensional gateway that allows it to jump instantaneously from one point of the universe to another light years away.
How?
Well, it's difficult to... It's all math.
Try us, Doctor.
Right, well, using layman's terms, use a rotating magnetic field to focus a narrow beam of gravitons. These, in turn, fold space-time consistent with Weyl tensor dynamics until the space-time curvature becomes infinitely large and you produce a singularity. Now, a singularity...
Layman's terms.
Imagine for a minute that this piece of paper...
No, excuse me. That's Vanessa and that's mine.
This attractive piece of paper represents space-time, and you want to get from point A here to point B there. Now, what's the shortest distance between 2 points?
A straight line.
Wrong. The shortest distance between 2 points is 0, and that's what the gateway does. It folds space so that point A and point B coexist in the same space and time. When the spacecraft passes through the gateway, space returns to normal. It's called a gravity drive.
How do you know all this?
I built it.
Smug, isn't he? And then the film shows exactly what happens when you try and cheat nature. Look at her face. She's not buying it. So anyway, here's a wormhole. It's a shortcut through space-time, and it is consistent with Einstein's theory of relativity. So it is theoretically possible. In fact, in 1916, Einstein teamed up with Nathan Rosen, and together they created a solution of relativity which included a shortcut through space-time. So say, for example, you're going through our universe. It might take a long time to get to here, but if you could make a shortcut, you could get there in no time at all. Or even this could be another universe altogether, another plane altogether. So it opens up extraordinary storytelling possibilities. And I feel that there's nowhere really it's explored to such good to such an extent as it is in the film Interstellar. I love Interstellar because it uses science as respectfully as possible for the story, mostly.
There, that's it. That's the wormhole.
You say it, don't spread it, Ron. It's a sphere. Well, of course it is. What you thought it would just be a hole. No, it's just that all the illustrations I've ever seen,
The illustrations. I'll show you how it works. So they say you want to go from here to there. But it's too far, right?
Mm-hmm.
So a wormhole bends space like this, so you can take a shortcut through a higher dimension. Okay, so to show that, they've turned three-dimensional space into 2 dimensions, which turns a wormhole into 2 dimensions. A circle. What's a circle in 3 dimensions?
sphere.
Exactly. A spherical hole. But who put it there? Who do we have to thank?
Well, I'm not thanking anybody until we get out of here in one piece, Ron. Everybody ready to say goodbye to our solar system?
To our galaxy.
Here we go.
Controls won't work here. We're passing through the bulk, space beyond our 3 dimensions. All you can do is record and observe.
So what we were seeing there as the ship approached the wormhole and the distortions around the wormhole, it's kind of what you would see. Kip Thorne's very respected physicist was a consultant on this movie, and he helped with visualizations. And it's one of the reasons why I love Interstellar, because it kind of tries to give you a sense of what that would be like. So wormholes again need huge energy requirements, the output of the sun at least, and they're also inherently very unstable. So the solutions to this would require exotic matter to keep the bridge stable, to keep the gateways open. Exotic energy, again, negative energy perhaps. I just have to say this again, I love this movie. So what about black holes? Let's move on. Black holes. Now this is an animation of Gargantua, which is the black hole used in Interstellar, used in the story. So let's have a look at what a black hole is. So when a star dies, a heavy star, much heavier than our sun, when it dies, it contracts. When all its fuel is used up, it collapses inwards, in itself. It becomes denser, heavier, until there's an almighty explosion, a supernova. And what's left swirls around and around, in and in again. And as it gets denser and denser, the gravitational force on its surface gets stronger and stronger until such point as even light cannot escape. That point here is called the event horizon. And the event horizon is the point at which light can no longer escape. The star continues to shrink inwards and inwards until it reaches a point called a singularity. Here, all known physics breaks down. Nobody really knows what goes on here. So a black hole would be a fairly, shall we say, risky way to cross space. We don't even know if it would go anywhere, if you would just get crushed at a singularity. But there are certain solutions to the equations of relativity, and some quantum ideas, quantum and relativity don't really work together. But they reckon there might be a possibility that this could lead somewhere else. But I don't know, I think it's fairly risky. I think I'll stick with the warp drive. But black holes were theoretical objects for about 40 years, until there was more and more evidence suggesting that they were real things. And then in 2019, this appeared. This is the first ever actual image of a black hole. So it was made in 2019 from the Event Horizon Telescope. And the Event Horizon Telescope is actually a global network of scopes that pull together thousands of gigabytes of data. And what we're looking at is a supermassive black hole in the center of the M87 galaxy. It is 6.5 billion times heavier than our sun. So what we're looking at here, this dark hole here, is the event horizon. It's not the black hole itself. That's inside somewhere. The event horizon is the point at which light can't escape. And what we're seeing around here is what they call the accretion disk. That's the gas and all the material that's being sucked into the black hole. And as it gets sucked in, like water down a plug hole, it goes round faster and faster until it glows white hot. And that's what we're seeing. Just as with this animation here. Again, this animation is based on actual physics. And it kind of, the Interstellar was 2010, I think. This was 2019. It does look like a blurry version of this, doesn't it? It's quite incredible. So this is at the heart of the M87 galaxy, which is 55 million light years away. Now, a light year is the distance light travels in a year. So the light from this black hole took 55 million years to get to our telescopes. I was about to say that's almost the time of the dinosaurs, but they died out 65 million years ago, but it's still a long time ago, right? It's extraordinary. And just this year, we got this image in March 2024. This is the supermassive black hole at the heart of our own Milky Way galaxy. In the constellation Sagittarius, so it's called Sagittarius A, and it's much smaller, thank goodness, than the one in M87. This one is 4 million masses. It's just a wee one then. Now, I want to stop for a minute and just talk about why I think science fiction is an important part of scientific development. It inspires us. It inspires the next generation. And good sci-fi does a number of things. It generates the story from scientific ideas. It's not just cops in space, like so many sci-fi shows are these days. It explores concepts and consequences as part of the story. So it's all part of the plot. And we can see this in Interstellar, but good sci-fi still has the human element, because at the end of the day, you know, the universe can't see without us. Carl Sagan said, "We are star stuff. We are the universe. We are made of dead stars. We are the universe conscious." So we need this. We need the human element, as well as exploring science and exploring science as storytelling. So I'm going to show you a clip of what I mean here. There's a clip of Interstellar, and it has some really good science elements in this. It's not just about exploration and adventure, although that's a big part of it. But there's a race against time in this clip. And there's a race against time because they're on a planet that's very close to a black hole. So relativity is kicking in. Time is different there. And so the gravitational tidal forces are far greater. So there are big waves afoot. If you've seen this film, you know what I'm talking about. But also I want to ask you to do something. Listen out for the clock. In the music, there's a clock ticking away here.
But Miller still looks good, though, right? Because she's coming up fast.
Mm-hmm.
With one complication. The planet is much closer to Gargantua than we thought.
Gargantua. It's what we're calling them, the black hole. Miller's and Dr. Mann's planets both orbit it.
And Miller's is on the horizon?
Oh, it's a basketball around a hoop. Landing there takes us dangerously close, and a black hole that big has a huge gravitational pull.
Look, I could swing around that neutron star to decelerate.
No, it's not that. It's time. The gravity on that planet will slow our clock compared to Earth's drastically.
Oh, how bad?
Well, every hour we spend on that planet will be 7 years back on Earth. Well, that's relativity, folks.
Very graceful.
No, but very efficient. What are you waiting for? Let's go. Go, 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 go. 7 years per hour here. Let's make it count. Wreckage. Where's the rest?
Towards the mountains!
Those aren't mountains. They're waves.
Oh shit. Oh shit.
That one's moving away from us.
We need the recorder.
Doyle, back to the Ranger now.
We're not leaving without her data.
Get back here now. No, we do not have time. The second wave is coming. We're in the middle of a swell.
I got it.
Get your ass back to the Ranger now!
I want to watch that again now. So there we go. So summing up, black holes, not a brilliant idea. Wormholes, too inherently unstable, but we might manage it one day if we get the right sort of matter. Warp drive is probably the most likely. But again, there's some real issues there, which I believe we will iron out eventually. So that's warp drive. That's faster than light. Briefly, because we don't have that much time now, I want to talk about time travel. I'll play you a couple of clips from some of my favourite time travel movies. This one from 1960, The Time Machine, probably the first best known time machine story.
It was disconcerting to see the sun arc in less than a minute. To see a snail race by. My flowers flinging wide their petals to embrace the new day. It became intoxicating. So I pushed the lever on toward even greater speed. As I went along, I gained experience in handling the machine. I found that I could stop for a day, an hour, or even for a second to observe. Then go ahead a year or two. Thus I was able to see the changing world in a series of glimpses. Good heavens.
Good heavens, I say. You'll see a lot more than that if he goes further forward. So, and then of course, one of the best, perfect time travel story, Back to the Future.
Doc, you disintegrated Einstein.
Calm down, Marty. I didn't disintegrate anything. The molecular structure of both Einstein and the car are completely intact.
Where the hell are they?
The appropriate question is, when the hell are they? You see, Einstein has just become the world's first time traveler. I sent him into the future. 1 minute into the future, to be exact. And precisely 1:21 a.m. in 0 seconds, we shall catch up with him in the time machine.
Wait a minute, Doc. Are you telling me that you built a time machine? Out of a DeLorean?
The way I see it, if you're gonna build a time machine into a car, why not do it with some style? Besides, the stainless steel construction made the flux dispersal. Look out!
Now, what's wonderful about this film is it's so well written. It is a perfect movie. But you see that frantic discussion that Doc Brown gave there whilst the car was travelling through time. It's perfect. It's perfect because it gives the audience an idea of what's going on and just enough of the science so that we know what's happening in the story and to get an idea of the science. It's brilliant. But I think my favourite time traveller is the Doctor. It's got to be. Ever since I was a kid, I've watched Doctor Who.
Come on.
No human's ever seen this. You'll be the first.
All I want to see is my bed.
Donna Noble, welcome to the creation of the earth. We've gone back 4.6 billion years. There's no solar system, not yet. Only dust and rocks and gas. That's the sun. Over there, brand new. Just beginning to burn.
Where's the earth?
All around us. In the dust.
Puts the wedding in perspective. Lance was right, we're just...
No, but that's what you do. The human race. Make sense out of chaos. Marking it out with weddings and Christmas and calendars. This whole process is beautiful, but only if it's being observed.
So I came out of all this.
Isn't that brilliant?
Oh, I think that's the Isle of Wight.
Eventually, gravity takes hold. Say, one big rock, heavier than the other, starts to pull other rocks towards it. All the dust and gas and elements get pulled in, everything piling in until you get
the earth.
But the question is, what was that first rock?
Look.
I want to watch that now as well. So, time travel. Is it possible? Well, it depends. And again, we need to go back to this guy, Albert Einstein, and relativity. So remember, in relativity, we're moving faster in space, but slower in time. So could we go back to the future? Yeah, sort of. If we go towards the speed of light, time slows down. So what might be just a year at light speed for us would be 1,000,000 years. So you could go into the future, you could travel into the future, but you couldn't come back. It'd be a useless time machine. What about travelling to the past? We could use a wormhole. Now, wormholes are shortcuts through space-time. Remember that? So not only are they shortcuts through space, they're also shortcuts through time. So perhaps we could use a wormhole. But there are a few teething troubles. There's something called the grandfather paradox, you might have heard of that. There's the closed loop paradox, and there's alternative timelines, unstable universes that we could open up and collapse. You don't want that. So here we have 3 ideas that are explored in sci-fi. So if you go back in time, say to shoot Hitler as a baby, someone else will take his place and World War II still happens. So it's a fixed timeline, and we see that in the Terminator, we see it in Harry Potter, we see it in 12 Monkeys. There's also the idea in a dynamic timeline where you can change events, like, but this gives rise to real paradoxes, like the grandfather paradox. If you went back to kill your grandparents, then you would never have been born. But then if you were never born, you wouldn't be able to go back to kill your grandparents. So that creates a paradox, something that can't really happen. Or you get caught in a closed loop where you keep going back doing the same thing forever and ever. You don't want that either. So the grandfather paradox was basically the plot of Back to the Future. You know when his hand starts disappearing? It's the effect. Or if we go back in time and change things, we change the timeline, so we create an alternative universe, which is a completely different world. And we see that in Terminators 2 and 3, we see that in Misfits. We also see it in Back to the Future 2, and in the Star Trek reboot. So philosophically, it's a no-no, but technically, could we build it? Sorry, no really. We need better physics before we can start mucking about with things like this. Relativity and quantum don't play nice. Relativity is the science of the very large. quantum physics is the science of the very small. They should work together, but they don't. That's the big problem in science just now. And if you think about it, the very big is made up of the very small, so why wouldn't it work? So that tells us that there's some better science down the road. Pretty exciting. We might also need better philosophies as well. I mean, we think the past is back the way, the future is ahead, or in some cultures the future's behind because we can't see it, and the past is ahead because we can remember it. But really, that idea comes from relativity, and it comes from old ideas as well. But there is also a philosophy that there is only the present. I want to leave you with this. There is only the present. The past doesn't exist because it's happened. The future doesn't exist because it's yet to happen. There are only infinitesimally small slices of now. Sounds like an echo. So there is only now. That's a thought. Which means, if that is the case, then we need to develop science to explore that. And as our mind evolves, so will our science, because science is a way of thinking. And as we think, we change our perception, we change our world. We are not passive observers of our universe, we're at the centre of it, co-creating things. Now, this is according to one view of quantum physics called the Copenhagen interpretation. It's contentious, but it's a beautiful thought, I think, anyway. And it's also at the heart of some ancient Eastern philosophies, that we are at the centre of our own personal universe and we can affect the outcome. So basically, the world really is what we make it. Will we change it for the better? How do we do that? Can we do that? If we live in some remote area, what can we do? We can change the world by our thinking. We all can do it. You might be the next person who develops that breakthrough. You might build a time machine, who knows? But keep watching, keep asking, keep wondering, and please, never grow up. Because kids make the best scientists. When you get to our age, we just take things for granted. Grown-ups can be a bit boring. So never grow up, keep asking. Thank you. Now, I do believe we're going to have some questions, is that right?
Yeah, Scott, thank you. That's given us so much to think about, quite literally. Apart from the fact I've now got my movie weekend sorted. So
yes,
I've seen Interstellar, and I know that I haven't. So you've put that right up on my list. Back to the audience, the viewers. If you'd like, you got any questions for Scott, please put those in the chat, and he'll be able to answer them. I've got one comment there that Dr. Alan Grant is a genius. Don't know if that means anything.
Dr. Alan Grant is a genius. Okay, I'll take his word for it.
Well, so here we go. So Morag Mackenzie has asked, what about memories and dreams? If we only have now, what about them?
Well, it's not that, I suppose, this is my take on it. It's not that these things didn't happen. They did happen, but there isn't a place to go back to. Yes, they exist in our memory because memory is mind. And they're just as relevant if there is no past or future. There is only now, but those nows did exist at one point. It actually makes our memories and our experiences, I think, far more valid, because there isn't some other dimension where they're still there. The fact is they happened, they were personal, and we keep them in our mind. I love that.
So there's a follow-up to that, is do they have energy?
Wow, that's a cracker. Do thoughts and memory have energy? I would say yes, because one definition of energy is the ability for work to be done. I remember being told that at school, thinking that's a cop-out because it's not telling you what energy is, but it does define it in terms of what it does. And if memories affect our mind, affect our memories, affect our love, that gives us energy to do things. That gives us the ability to do things, the inspiration to do things. I would say that's very much energy, yeah.
I would do, actually, it makes sense now, and I did know this. The Dr. Alan Park, he was the actor from Jurassic Park in the movie. So that was just to clarify who Alan Grant was. I did know that. So there's a really good question here. Neil's character mentioned that magnetic fields could affect gravitons. can gravitons interact with magnetic fields?
It's a good question. I'll get back to you on that one. In other words, I don't have a Scooby. Gravitons are hypothetical. We haven't, as far as I know, they haven't been detected yet. I think the closest we got to that was probably the Higgs boson, which is a particle that was discovered just recently, actually, in the last, 10 years, which explains why we have mass. But I don't think it explains... I don't think it explains gravity in a particle sense. Yeah, sorry, I don't know the answer to that.
If the answer comes to you, I know who asked that question, so I can pass it on. So I was on here, I was going to say was perhaps an easier one, but we've had a whole presentation on this at our live science festival, and it is, what is your favourite science fiction movie?
Oh, that's impossible to decide. It actually depends on the night, to be honest. I think Interstellar is definitely one of my favourites because it does make a serious attempt at using science visually and narratively, exploring science as part of the entertainment, as part of the narrative. So I think that's definitely one of my favourite. 2001, of course, was brilliant. Its sequel, 2010, was really good as well. That's lesser known. Oh my word. Oh, I'll definitely have to get back to you on that one. There's so many.
I think at the live one we did, the discussion was mainly between Back to the Future and The Wrath of Khan were the two that were being debated. So
actually, they're definitely in my top 5. Yeah, I would say both of them.
So we have one in the Q&A as well. Do you believe there is a multiverse?
Oh, that's a good one. I don't know. Because, I'm not sure if I fall into the camp of there is only the now, or the general relativity idea that the past and the future is some when to visit. Quantum theory, quantum physics, there were sort of two main interpretations of quantum physics. There was the Copenhagen one, which was about how the observer affects the outcome of things. So it puts the observer and the external world interdependent, and that kind of ruffled a few feathers, I think, because I think a lot of science came from Newton, which was about classical clockwork universe. It's out there, it's being observed by us, but quantum physics suggested that we are actually at the center of things, that we have an active role in the outcome of things. But another way of explaining quantum physics was the many worlds hypothesis, the multiverse, basically. So that if an outcome is observed, there's actually a branch off of that into a parallel universe where the other thing happens, and the other thing, and the other thing. So at any given moment when a decision is made or something happens and something is observed out of a possibility of outcomes, all these outcomes happen, but in different universes. It seems a little messy. I don't think the multiverse really works, simply because there's a very simple scientific tenet called Occam's razor, and I love Occam's razor. It basically states that all things given, the simplest solution tends to be the right one. And it just seems a little messy of the universe to have universes branching off willy-nilly every time something some outcome out of a possibility of outcomes happens. So yeah, I'm not certain. I don't think so, actually.
So there's another one here. It's like the concept in Ant-Man, where you could go to subatomic level. Is it where? It's, I think, could you go to the quantum level?
I haven't actually seen Ant-Man, but yeah, that's one on my list. I definitely need to see Ant-Man. I didn't know he went down to the quantum level. That's interesting. I'd like to see how they visualised that, actually. Could you go down to the quantum level? That's an interesting question. Like kind of like a warp bubble. If you could cover yourself in a bubble and then... I don't know, but I think my suspicion is that the lower down you go, down towards the the Planck length, which is what we were talking about with the vacuum energies, the universe would become more and more granular, pixelated. You would be going down to the basic pixels of reality, which is down at the Planck length. So the universe would be in very low res down there. I'm not sure you'd see much, if at all you possibly could.
So we've got one here. If light travels at the speed of light, does it experience time?
No, it doesn't actually. If you were a photon, you wouldn't experience time at all, because you don't have any mass, you're traveling at the speed of light, and so on that space-time diagram there's nothing going in the time direction. So light, no, light doesn't experience time.
So we've got here from Nick. He says, I saw something that said that real matter only makes up a small percentage of the universe, and dark matter added to this adds up to 25%. So what and where is the 75% of dark energy in the universe?
It's a very good question. We don't know. We don't know yet what's going on. Yeah, 5% of the mass of the universe is observable. So stars, galaxies, people, planets, that kind of thing. But because of the way the objects in the universe are moving, that tells us there's something else going on there. And the way the universe is moving, only 5%, what we see only accounts for 5% of the influences out there. So that's why they sort of came up with the idea of dark matter and dark energy. Dark energy is actually the force that is pushing the galaxies apart. So after the Big Bang, the universe flew apart, but that expansion is actually accelerating. You've been trying to fine-tune this through observations and so on and so forth, and yeah, it looks like the universe's expansion is accelerating. Things are getting further away from us faster, and that repulsive force is called dark energy. As to what it actually is, it's a good question. Ask Brian Cox, he might know.
Plenty of research there.
There's a lot of research. Actually, it's a very good question, because it's one that is trying to be answered just now. Yeah.
Well, what do you think the next giant step? You talked about how fairly recently they've photographed a black hole for the first time. What do you think the next thing is that we'll see for the first time?
I think the next big thing will be an actual photograph of another planet. At the moment, I'm trying to think of the name of the telescope. Damn it, it's escaped me. But we've found thousands of extrasolar planets, so planets orbiting other suns, but we've detected them indirectly. So at first it was only big, heavy Jupiter-like planets, because it was causing drag on its star, and we could see little wobbles of stars. So Hubble,
the James Webb Telescope.
The James Webb Telescope, yeah. So, but we also can detect planets other ways. If a planet moves in front of its star, the star will dim slightly, and we can tell with how frequently that happens. We can tell if something is orbiting it or not. So those are two ways, but they're quite limited ways. And I think one day, will Webb be able to directly photograph another planet? I think it might have done already, actually. Yeah, I'll have to brush up on this, actually, but I think that'll be the next big thing. Also, if we can photograph another planet, an Earth-like planet orbiting another star, and if we see the refraction of sunlight through that atmosphere, we might be able to detect what that atmosphere is made of. And if we find certain chemicals in that atmosphere, if we find free oxygen in that atmosphere, that will show us that there's life, or something there that's generating free oxygen. Because oxygen is so radical, it will interact with anything. And so the very fact that there's oxygen, if you were passing Earth in a spaceship and you went, oh, there's 20% oxygen in the atmosphere, that's only there because life creates it. More specifically, it's only there because the forests create it. And you know what's happening to them. So there's a thought. But yeah, if we could find free oxygen in another planet's atmosphere, that's proof there's life.
That's exciting things to come then.
I think that'll be the next big one. In fact, I'm going to put myself on the line here. I think we're going to find proof of other life within 10, 20 years.
That's good, because that was the next question I was going to ask you from the Q&A is, do you think intelligent extraterrestrial life exists? And if so, will you ever contact them?
Depends who you talk to. Brian Cox thinks it's highly unlikely. He thinks life is abundant. But intelligent life, sentient life, life that has evolved to the stage where it could send radio signals to us, he thinks that's incredibly rare. In fact, we might be the only ones out of 400 billion stars in this galaxy. I'm a little bit more optimistic. I think the conditions on the Earth are very rare, but they're not unique. And there are 400 billion stars in this galaxy. Nearly all of them have planets. So chances are that the conditions on Earth have been reproduced elsewhere, and chances are that a civilization has appeared. Thing is, though, has that civilization survived its own technology to be around long enough to talk to us? That's a question we need to ask ourselves as well. Will we be around long enough to talk to them? You see, this is why this stuff fascinates me as well, because it has direct application to our everyday life. It makes us think. It makes us think about ecology, about politics, about our place in the universe, how we treat each other. You know, it puts us in the centre of things. It's very quantum.
So we've got another question here from Ojas. Says, I think a black hole, as you said, has a singularity. But if energy can't be destroyed when a black hole takes in matter, does it come out of a white hole, maybe?
Oh, a good one. I'd like to think so, because then you could travel through it. I don't know. Black holes do get bigger. It collects matter. So black holes get bigger, but it also sheds some energy as well. Because of the uncertainty principle, actually, some energy leaks out. And Stephen Hawking, I think he won a Nobel Prize for this, actually. He theorized, and it was detected. They detected Hawking radiation. And so eventually a black hole won't just grow and grow and grow indefinitely. It will eventually evaporate because all its energy will have drifted off. But that will take quintillions of years, well beyond the last star has died out, that will happen. Black holes will eventually evaporate. As to a white hole, is the singularity rotating or is it not? Is it a point? Is it spinning in a donut shape? Who knows? But some have speculated that it could lead to a place in the universe where matter is leaving. In other words, a white hole, not a black hole. But yeah, I'd like to think so.
And we'll go for one last question, mainly because I'd never thought of Groundhog Day as a sci-fi movie before, but I guess it is.
Yes.
Yeah, but I suppose theoretically it is. It says, what do you think of the conscious time travel in The Edge of Tomorrow or Groundhog Day?
Now, I haven't seen The Edge of Tomorrow, so I'm afraid I can... oh my goodness, I've got a lot to catch up on. But Groundhog Day, I suppose, actually, you could think of that as a science fiction movie. The only thing, really, that stops it from being a sci-fi, I would say, if I was to play devil's advocate, is that there's no actual scientific motivation in the story to cause the loop. It's actually entirely internal, it's personal. It's quite a spiritual movie, actually, but because it's using a closed loop time as its story, yeah, I think you can argue it is sci-fi. That's a great one. I like that.
We'll leave it there. If there's any questions that we haven't answered, we will pass those on to Scott, and then anyone that's registered for the event, we'll not only send you a link to the recording, but we'll send you any answers that there are to the questions. So it's just one comment popped it there. It's just a thank you, but we'll pass all the thanks and comments on to you as well, Scott, rather than go through them now.
Okay, thanks everyone.
Scott, thank you so much for that. It truly was fascinating, and just wished, well, yeah, you know, my physics teacher. I wished he'd have made it as interesting as you have done.
Thanks. I've absolutely loved this. It gave me a chance to completely geek out and talk about it uninterrupted. So thank you. Loved it.
we really do appreciate that. Just before everybody disappears off, we will put a feedback link in the chat. This is the first time we've run the Scotland's Digital Science Festival, so please do complete the feedback form and let us know what you think. Let us know what you would like to see in next year's event. So we have set the date for next year's event. It will run between Friday the 21st and Friday the 28th of November. So keep a watch out for that. If you've enjoyed this evening, and certainly I have, then have a look at our programme. We still have a few more events. Tomorrow we have a guy who's also spent a bit of time in California who will talk about AI and how it can control behaviour, and a little bit of conspiracy theory there as well. And then finishing the festival tomorrow night, we have an over 18 quiz by some professional quizsters that we think everybody will enjoy. So please sign up for that. But thank you so much, everybody, for joining us. And Scott, thank you.
Just realised I forgot to mention one thing, just very quickly. Remember I asked you to remember the clock, to listen out for the clock when they were on that planet in Interstellar. Each beat of the clock represented one day on Earth. So it's a hard science was coded into the music as well. Sorry, it just occurred to me.
That's your sound editor piece coming in there. So
that's it. That's my sign off.